Silicon Valley Leaders Symposium this semester. And before I introduce our speaker, I will urge you to look up SVLS, SJSU, because I can't remember the date of the next one. The third person in our series is Daniel Andrews from NASA. I'm not sure I'm getting his last name correct, but in any case, he's the guy behind the Viper robotic mission. So he's got a little bit different focus than what we heard about today. We're trying to keep a variety of people. And our speaker today, he represents a rare combination, a technology pioneer who helped to build Silicon Valley, and then an educator who has shaped minds at Stanford for 4 decades. And then lastly, a visionary and determined to transform children's healthcare worldwide. So a little bit about his background. Dr. Timothy Chou, he got his BS in electrical engineering at NC State University, and then his PhD at the University of Illinois, Urbana-Champaign, or Horn and Flat. And he started his career at one of Silicon Valley's very first startups, Tandem Computing, and then he went on to become the first president of Oracle's cloud computing business, literally inventing the category that would transform how the world uses software. Tim is equally passionate about his teaching career. For over 40 years, he's been on the faculty at Stanford University. His dedication to students is legendary. He once taught core computer science for 15 years straight, not missing a lecture, only taking a break because he had to fly to Bali for a sales meeting and then get back within 36 hours. Come on down, to teach his next class. After retiring from Oracle, he returned to Stanford to create the world's first course on cloud computing. And it was a student in that class that changed everything. The conversation inspired Dr. Chou to come out of retirement.
Hi, how are you? How are you doing?
With this initiative to reduce healthcare inequity and to improve outcomes for children everywhere by building privacy-preserving AI that connects data from all 1 million healthcare machines across 500 children's hospitals in the world. The executive director at Scientific American commented, "The project starts with children's diseases, but it can be scaled to include all diseases and all patients in the world, providing knowledge and expertise beyond the ability of a single individual. This may be the greatest innovation in the history of medicine." So with that, please join me in welcoming Tim.
Before I kick off, I'm just kind of curious, what majors are you guys? What are you? Just AI. Okay.
What?
Wrong room.
Oh.
292. Where is 292?
I think it's probably down that way, but I don't know.
Electrical.
In the back, She's quite,
Do we not?
yeah, the person in the gray coat.
AI.
AI, okay, excellent.
It's a master's program?
Yeah, we have an MS in AI, it's about 5 years old. Yeah.
Okay. So I'll start out by saying I always start out my Stanford class with the same thing, which is the mark of a great student is not measured by what you know, but by the quality of the questions you ask. So learn to ask good questions is part of what I teach now. So I'm going to do a lot of talking here, but what I'm really interested in is questions from you guys, okay? So I'm not going to try to occupy the whole time. I titled this talk Terminator or a Star Trek Future, because I think when you're paying attention to all this discussion about AI, you kind of you can see both sides of this conversation going on. And so I want to take you through at least my journey in the world of healthcare and how I believe AI could be a Star Trek future. I'm going to talk technology. We've engineered the world's first distributed AI cloud infrastructure. I'll go into that in some depth, and obviously, if you guys want to go deeper, great to do that. And then talk a little bit about what all of this might mean in the future state. So I appreciate the kind introduction. I actually I just did a posting called The End of SaaS, because I wrote this book, The End of Software, 21 years ago when I was president at Oracle, to talk about really this transformation of software being not delivered as a CD-ROM, but delivered as a service. And then, yes, we started this class on cloud computing now 15, 16 years ago. I do the first and last lecture. In between, I have guest lectures. They're all CEOs of public companies. We've had a who's who walk through there, CEOs of Salesforce. We just had CEO of Pure Storage. We had the CEO of Zoom, Eric Ren. He came actually in 2019. I'm pretty sure it was the last lecture of that year. And if you all remember history, that is like before Zoom became a verb, an adverb, and a noun. So it's been a lot of fun. I only teach this class once a year because basically I'm a giant executive assistant scheduling people. Because I'm going to talk about data centers in a minute. We built one of the very first data centers in Austin, Texas to house all the computers when we were delivering the very early days of the Oracle Cloud infrastructure. I'd like to start out with hoping that I will teach you a few lessons for long life in your career, but if not, here's a few lessons for long life in your personal life. Okay, some of you can read this. This is actually taken from a temple in Kyoto, Japan. It's believed to be the 10 lessons for long life in your personal life. For those of you who are not reading Chinese yet, here's the rough translation. I'm sure this will be true at lunch. We're supposed to eat more vegetables and less meat. You're supposed to have more sleep and less worry, more action and less words. And then the one I've always found amusing, the more bathing, less clothing. So you got to imagine Buddhist monks 500 years ago, right? They didn't have much to do. So maybe this was entertainment in their world. So like I said, if there's nothing you get out of this, maybe you can take away a few lessons for long life in your personal life. As I said, there really are competing visions of the future for artificial intelligence. Some people see a Terminator future, and I think a few of us see a Star Trek future. I will leave you to debate which one you think we're headed into. As I said, I wanted to give you a little bit of a glimpse into what are the real-world healthcare challenges out there, and to also explain the origin of all of this. So I said I teach this class at Stanford. About 10 years ago, a strange student signs up. He has an MD, an MPH, an MBA. He's chief of pediatric cardiology at the Children's Hospital in Orange County. He wanted to go out for breakfast, and I went, okay. I was thinking, I'm looking at him going, I don't know anything about pediatric cardiology. Why are you taking this class? And he goes, well, I really believe that AI, big data, and cloud computing need to be medicine. And so I am here to get a master's degree in bioinformatics. I like to tell Anthony's story because I'm pretty sure he's like 53 years old at this point in time. The program at Stanford is probably one of the leading programs in the country. It takes them 3.5 years to finish a 2-year program because number one, he has no idea how to code. Number two, he has a real job. He's chief of pediatric cardiology. And number three, he decides at the age of 52, 53 to adopt an 18-month-old and a 6-month-old, and he's a bachelor. So I always tell people the story because it's never too late for any of us, right? One of the very first stories Anthony told me is really a story that it was him. He was providing consulting for a little girl in Myanmar who had a cardiac condition. They wanted to share the ultrasound image with him so that he could provide his advice on it. They didn't know how to do that. They couldn't do that. Ultimately, she actually died on the operating room table. Later on, he did get to see the ultrasound. He said, well, I could have actually told them what to do. Bring it a little bit closer to home. There's a whole class of diseases called congenital heart diseases. They actually represent 24 different anatomical defects in a heart. One of them is just crazy to think about. It's a child born with a single ventricle. Another one is this one, which is called the transposition of the great arteries, which is that the arteries are flipped around. The result is the baby is born blue. This is a story actually, like I think in Salinas. This kid was not diagnosed prior to being born. Was born with this transposition of the great arteries. They had to send in a catheterization doctor to try to stabilize her, and then flew her up to Stanford for surgery. That's like right next door to us, right? This isn't, you have to go to Myanmar. If you look at a global picture in pediatric healthcare, interestingly enough, we have 3 states in the United States that have no pediatric emergency physicians whatsoever. 60% of the rural hospitals, the rural communities in the United States have no pediatric expertise. Cardiology, oncology, any of this, 0. We have about 3,000 pediatric cardiologists in the US. What I just explained to you is that they're mostly living in the major metros. In India, there are 300 pediatric cardiologists. In Rwanda, there is 1 guy. Okay? Again, you don't have to go very far. This is actually in Willits, California, which is north of here by about 4.5 hours. The Adventist Health is the hospital in Willits. There's no pediatric expertise there. The population of Willits is about 5,000. 20 times a month, they ship a kid to UCSF or Stanford or UC Davis or the Shriners Burn unit because they have no expertise. So this is sending air taxis, this is ambulances. In fact, they even figure out at what point in time the kid is going to try to figure out the local traffic to decide whether they're going to send them to UCSF or to Davis to avoid traffic. I mean, again, this is in our neighborhood, not very far away, right? The level of expertise is pretty much 0. This is actually a story from Southern California. There was a kid who got hit on the head in some playing in some game. They took him to the local hospital, and they said, well, you know, we ought to CT scan him. They CT scanned him. They said, no, he doesn't have a concussion. And they sent him home. A couple weeks later, he's still having symptoms. They go, let's go to, and they went to a children's hospital, I won't name it, in Southern California, re-CT imaged him. He doesn't have a concussion, sitting home. X weeks later, he still has the problems. He goes to a 3rd site. Now, make one point. They are re-imaging him every time, right? They're doing it every time. The 3rd time, they go, oh, he doesn't have a concussion. He has a brain tumor. Okay? This is also showing you something about confirmation bias in humans. You go into an emergency room, you say you get hit on the head, the automatic expectation is, what, you must have a concussion. So I'm going to go look for a concussion. You don't sit there and go, I'm going to look for a brain tumor. Give you another story. This is out of Texas. A little kid in West Texas goes into an emergency room with a fracture. The local people come to the conclusion that this is child abuse. Law enforcement is called in. The kid is actually taken to Texas Children's in Houston. He's re-x-rayed, and they come to the conclusion that, no, this is not child abuse. And just imagine all the family has gone through, the kid has gone through, because the humans didn't really call this correctly. We'll go to more rare conditions for you to think about. This is a condition called focal cortical dysplasia. It's actually a brain lesion, a little spot. In fact, just so that's focal cortical dysplasia, a little spot in the brain. If left untreated, the kid has epileptic seizures. There's a kid in Florida that for the past 12 years, 2 to 3 times a day, and at night, he has seizures. At night, he wakes up screaming, and this has been going on for 12 years. They MRI imaged him very early in the cycle, didn't see anything. They ended up giving him a ton of drugs, some that they could afford, some they couldn't. They were getting ready to actually put electrical implants into the brain. They re-MRI imaged him, and now they're pretty sure he has this condition. Now, what's really cool is, if you diagnose that, you can actually surgically remove that spot, and the kid is cured for life. So good news, bad news. Good news, this only happens 25,000 times a year in the United States. Good news. Bad news, no one pediatric neuroradiologist sees enough of these conditions to get any good at being able to diagnose this sort of thing. I'm going to bring you into the world of medicine, of pharma, biopharma. This may surprise you. In 2024, there were actually more what are referred to as orphan therapeutics approved than non-orphan. And orphan actually doesn't have anything to do with kids being an orphan. I'm not even sure why they called it. But an orphan therapeutic is a therapeutic designed for only 200,000 people or less. This actually is exhibiting what we've all known as a long-term trend in biopharma, which is the progression towards building personalized drugs, personalized medicine. So we're out of the world of building drugs for 200 million people to the world of building for 200,000 to ultimately 20,000, 2,000, et cetera. There are huge challenges in this. I mean, the chemistry, biology is advancing at furious rates. Actually, in a lot of ways, we had the CEO of Johnson & Johnson in my class a couple of years ago, and he said the whole thing with Operation Warp Speed and the push for a COVID vaccine just advances state of the art in mRNA and digital chemistry and digital biology. And he says, you've seen nothing yet. So we're still at the very early stages of what can be done here from a science point of view. The hard part of the problem here, though, is that if I'm building a drug for 200,000 people, first of all, how the hell do I find them for the approved drugs? And if you're familiar with what happens for new drugs, you have to go through what is referred to as a clinical trial. So if I'm only building something for 200,000, how do I find the people for a clinical trial? This has big implications from an economic perspective to the world of biopharma. Just to give you a sense of it, we are already tracking, these are 60 different rare conditions. I will later on talk to you a little bit about FSGS. These are 60 different rare conditions for which, in the past 2 years, therapeutics have been approved under orphan therapeutics for all of these. Okay? And clinical trials, I mean, if it is so primitive what they're doing today. They write a protocol document, which is like 90 to 100 pages of text describing inclusion and exclusion criteria. They go to a few sites that have what are termed clinical trial supervisors, and they hope that they're going to run into enough people, kids, whatever. Meantime, out in the rest of the world, here's a dad that's basically posting on LinkedIn, to try to find a clinical trial. I mean, again, super primitive. I'm going to end a little bit back in the world of global. You may not recognize this, but by the year 2050, Africa will be home to 1 billion children. 2 in every 5 children in the world are going to be born in Africa. So if we're all sitting around thinking that, oh, we're going to build a lot of medical schools and hospitals and whatnot to deal with that, I think everybody's like sadly mistaken. We have to think about this completely differently. Africa, if you've been a student somewhat of it, you already know that they leapfrog in telecommunications. They didn't put a bunch of landlines in, right? They're running cellular on day one. The giant potential for what could be done here in pediatric healthcare is, you could argue, both possible and the other side is mandatory. All of this went to the fact that right around COVID timeframe, I'm sitting around thinking I'm going to watch Netflix all day or maybe do something useful. And so I grabbed a group of engineers, people I've worked with in the past, and we gave ourselves a mission. And the mission is to reduce healthcare inequity, lower cost, improve outcomes for children, locally, rurally, and globally. How are we going to do that? By creating real-time, privacy-preserving AI applications based on access to data in all 1 million healthcare machines in all 500 children's hospitals in the world. That is what we call the Pediatric Moonshot. And you can learn more at pediatricmoonshot.org. We thought we'd come to the conclusion we named it correctly. I'm going to now branch over for the technical part of this conversation. So as with the original Moonshot, we came to the conclusion you need to build a new rocket to get to the moon. As you all are probably very well aware of, the OpenAIs, Claudes, Geminis of the world are all based on a centralized model of computing. I'm going to bring all the data into a giant data center in Louisiana, and I'm going to put a terawatt of power out back, and I'm going to learn on all that data, right? That's the currently accepted way to go do this. And by the way, it works just great for consumer data. Just to give you a sense, you may or may not have thought about this, the amount of data that this is being trained on is actually not enormous, right? GPT-4 was just trained on 1,000 terabytes. Just to give you a sense of scale, the 500 children's hospitals, only in the cardiology department, generate 6 million terabytes of data a year. Just the 500 children's hospitals, just in cardiology. I mean, the scale of data is massive compared to all this text data that's being used in the world of consumer. And we know data is prevalent everywhere. Real-time data coming out of clinical machines, ultrasounds, blood analyzers, bedside monitors, etc. Data coming out of research machines, next-generation sequencers, mass spectrometers, etc. Data coming out of PACSs, for those of you who don't know, these are hunks of software that are used by radiologists to go look at these images and annotate them, etc. And then there's data sitting in the electronic medical records in our world, largely in Epic and Cerner. And oh, by the way, the data is located all around the world. Enormous data sets, diverse data, located all the way around the world. But we came to the conclusion, which is the centralized model is never going to work for healthcare and life science. You're not going to bring all the data into a giant data center in Louisiana. Number one, I just described it, these data sizes are much larger. Number two, there are much tighter security requirements. And number three, much stricter privacy. Norway's already saying we're not letting Norwegian data leave Norway, just as a simple example of that, right? So we said, this is kind of CS 101, rather than move the data to the application, let's move the application to the data. So we engineered what we call a distributed AI cloud infrastructure, which literally puts a cloud server inside the building of a clinic, a hospital, a research lab, an ambulance, or the home. It is enabled, remember I said we wanted to build real-time systems. And the only way to get, and I'm just going to pick on ultrasound, the only way to get real-time data from an ultrasound is you have to be on the network with the ultrasound. There's no other answer to that. And so we engineered, you can imagine the very first time we had a conversation with the IT group at a hospital. They immediately said NFW, which you probably know what that means. But we kind of knew this going in, that would be the case. We engineered over 30 security and privacy features in that. These all are part of what, if you want to think about, for those of you probably all speak AWS, internally, right, we call this BWS, because in a lot of ways it mimics it. So we have compute, storage, networking services, etc. What is probably unique is the ability to now bring data that's from an ultrasound or a blood analyzer or an EMR record, which we do with what we refer to as a digital twin of that data source, which then provides that data to applications. So it's very much an infrastructure play, right, where we're saying we're going to free up the data from the ultrasound, the blood analyzer, the EMR record. You go build oncology applications, cardiology applications, neurology applications. So when I'm talking to a not technical audience, I tell them this is a lot like what Apple did. So Apple created infrastructure called a phone, shipped it around the world, gave people access to a camera and access to GPS, and then told the world, go build Uber and Lyft and Instagram. Very similar, although, you know, obviously our camera is an ultrasound as an example, or a blood analyzer, but the applications are many and diverse, and I'll talk a little bit about that in a second. I made mention we've engineered a whole bunch of different features. This is a long list that is part of a longer presentation. This is just to give you a little sense of machine digital twins. So we actually create a twin of, and I'll use Philips as a manufacturer of ultrasounds. So the digital twin for the ultrasound from Philips basically runs from everything from their portable Lumifys, portable ultrasounds, all the way to their big clinical Epic 7s. And the data reflected into the digital twin is not only static data, like, well, what's the serial number of the machine, dynamic data, what's the last error codes this thing threw out, environmental data, you know, where is it located, what's the temperature in the room, and then finally what we call gnomic data, so the actual echocardiogram or the actual blood analysis, et cetera. Right? So with this, we said, okay, there are, we'll call it 3 broad applications for this infrastructure. One is fairly simple, which is image sharing. We actually did a demonstration. Anthony is a pediatric cardiologist, Children's of Orange County. His oldest daughter, remember I said she was adopted. She has a complex congenital heart problem. He brought her into the echo lab at Children's of Orange County. The head of cardiology imaged her heart 6,000 miles away in Bambino Gesù in the Vatican, where her godmother works. She got to see her heart beating in real time. Okay? Super simple application of this kind of infrastructure. The next class of application is really inferencing applications. So, hey, you know, I have built a brain bleed analytic that runs in real time on every CT scanner. So now I can look at every CT scan that comes in and let the agent say, oh, you know, this person really needs to go to emergency surgery, what we call a red, oh, there's nothing really wrong, or yellow, hey, somebody probably ought to take a look at this, right? Okay, so that's all inferencing. I've already built, right, the AI application, the AI agent. I'm just executing it in real time, right, anywhere in the world. But the reality is that most of these applications out in the field don't really work that well. We are actually tracking right now 175 different research projects around the world. I sub-segmented this in the world of pediatric cardiology. These are research projects at like UCSF, at Stanford, at Mount Sinai, at UCL, all around the world, where the researcher has gotten hold of 1,000 echoes, 500 MRI images, et cetera, and built a multiple sclerosis diagnostic algorithm, have built a congenital heart disease algorithm, et cetera. They share a common thread, and you'll see it here. These are all in echo for pediatric cardiology. So you can see UCSF trained on 107,000 images. The second one trained on 108 patients. The third one at Boston Children's trained on 92,000 ECGs. Here's a set, 121,000 4-chamber views or ultrasound views, 7,300 echoes. So all small data sets. What these all have resulted in is people will publish their result, their beautiful rock curve, in Nature magazine, and then it just sits there. It doesn't do anything useful. And we all know that while it might have worked on the test data set, go take it and run it in the wild, and it's probably not going to work very well because it's all trained on small data. So, and this is just, that was the third one. This is actually a paper that got written about 2 years ago. Matt Lundgren was at Stanford, went off to Microsoft, Pronounced over at Harvard, and they basically looked at all the stuff that was out there, and I'm now not even talking about pediatrics. all of medicine and said, you know, basically, nothing works very well because they're all trained on small data sets. The model, the test data set, yeah, but not in the field. So, which leads us to, you know, the question of, okay, so if you don't put all the data in one giant data center in Louisiana, how do you solve this problem? So it turns out our friends over in Consumer have been working on this for a while. So you may not realize this, but Siri works this way. So Siri is trying to learn to recognize your voice better. Well, does it take your voice and send it to the Apple Cloud? And the answer is no, because number one, what about privacy? And number two, who's going to pay for the data transfer, right? So instead, right, they pioneered, and actually Google Keyboard works this way too, they pioneered the idea of federated, distributed, some people call this swarm learning, but all of these are basically the same technique, which is, can I learn on the data locally, right, on your phone, at that ultrasound at UCSF, and then only aggregate what I learned, right, which all you're transmitting out or sharing is a bunch of floating point numbers, a bunch of neural network weights that you then aggregate together to form the next generation of the model. We've done early work in medical imaging that says that this can work in medical imaging. There are 2 research groups in Germany who've also shown this, so we're all pretty sure this technique can work in the world of medical imaging. And I'll get down to where we're going with that next. But so we've been working a lot in imaging, but I want to introduce the last thing that we've been pushing, which is, right, we've been creating digital twins of machines, but we said, well, we could actually create digital twins of people or patients. And so early on, we sat there and went, well, you know, our servers are sitting inside the firewall, remember? So I could touch the EMR record. So we went and we said, okay, let's go grab an EMR record. And we started in oncology. You probably never thought about this, but these EMR records for a cancer patient, they could be 3,500 to 7,000 pages of PDF. Right, just for sense of scale, a box of printer paper is 5,000 pages. So there's a lot. Basically today, their primary means of looking at that data is a search bar. So imagine 7,000 page PDF document with a search bar. I mean, what can you figure out? Which is why, and everybody's experienced this, you walk into a doctor's appointment and they treat you like the database. Not because they don't have the data, but because it's so hard to get a hold of it. So we did something super simple. Remember, our servers are sitting inside the firewall. We pulled the PDF of the EMR record. We trained a local large language model on it. And now you can basically ask it anything you want. We shared this with 12 oncology nurses around the country. And because we knew we could do this technically. We had no idea if it was useful. And then we learned things like a oncology nurse, a chemotherapy nurse, before a chemotherapy will spend 15 to 20 minutes trying to figure out how much of the chemo drug was given over the past 2 times, 3 times. In this, it's just simple. You ask it, right? How much chemotherapy was the patient given? Right? So we've taken that and we're saying, well, you know, that's just part of the picture of what a patient is the EMR record. And we're right now in the middle of figuring out how do we bring in the data from the home. And in particular, we're using Fitbit as a way of a stalking horse for how to do this. So we're creating Fitbit digital twins, which model creating wearable digital twins. So now you can conceptually see that a patient digital twin can be composed of both the information coming out of the clinic, the ultrasound, gene sequence, EMR record, as well as data that's occurring outside of the clinic. How well did they sleep? What's their blood pressure every day, et cetera. So how could this be useful? Well, yeah, it's useful for productivity, but where it's really useful is, remember I said, the world of pharma is building increasingly targeted, specialized therapeutics. And I'll show you an example for FSGS. FSGS, turns out it's a rare kidney disease for which there's like 2 approved therapeutics. So the question becomes, well, how do you know if a patient has FSGS? It's fairly rare, and for any of these, C3G, HAE, SMA, these are all examples of what we call disease-precise digital twins. I'll show you, I think I put it in there, I'll show you an example at the end of FSGS, but here's the basic idea. For FSGS, which I'll show you, there are 34, to use fancy words, multimodal biomarkers. Not so fancy words, 34 queries that you ask the patient digital twin, to which we have a affirmative answer, yes, no, yes greater than 3, which adds confidence that the patient indeed has FSGS. We let these agents run in the background and grade the patients across the entire database. And then if they score greater than 90, we put something, the medical record says, look, here's the 34 reasons why we think this patient has FSGS. Here are the 2 approved therapeutics. If it scores under 50, you go, eh. If it scores between 50 and 90, you could put in the medical record, hey, you know, might have FSGS, and we can rank order the cost of the test to go, you should probably send them in for a urinalysis, okay? The corollary to this, remember I said, is the trial work. So how do you find patients for clinical trials? As I kind of indicated to you, today's method is the drug company ships a 120-page PDF document. The clinical trial person at the other end reads it, goes and looks at the EMR record and goes, we're like, that's stupid, right? So basically, we can create trial-precise agents. Trials are generally about inclusion and exclusion criteria. So again, you can imagine a set of inclusion-exclusion criteria for that particular clinical trial. The clinical trial agents can run in the background and grade all the patients as to whether they're trial eligible. Furthermore, you can do things they've never been able to do before. So clinical trials today, when you look at the protocol, it's like, why is that the protocol? When you talk to them, it's largely historic. They don't have, because they're not operating with any real data. So here you could go, well, I'm going to design a trial, and I'm going to say everybody in the trial has to have blue eyes. I could run the trial agent, just runs in the background, and it says, oh, there are 10 people that would qualify. Then I could change it to, how about brown eyes? And it says 50. And I go, oh, I can now design my trials, right, which they've never been able to do. We are in the process of putting all this into action. I told you that we have already built zones in 8 sites on 3 continents. The next major step is what we are calling an AI supercomputer for children's medicine. Roughly with 32 sites, all imaging machine data available in real time, all PACS data, all EMR data available, roughly 3,000 servers, roughly 2,000 terabytes of data flowing through it annually, and roughly 6 million, what you just saw, patient digital twins. I've been funding all of our work to date. This next step is rough 50 million. And so we launched a capital campaign late last year. And that's, your dean just read the quote. We did the event. I can share the video. The interviewer is the executive director at Scientific American. I tell you, when you watch the video, it's kind of funny. He starts out being kind of like this disinterested third-party character. By the end of this presentation, he's going, he says, how can I help you raise money? And he actually posted this in LinkedIn, which I thought was a little over the top, but we're willing to take it, right? So a quick glimpse, let's assume we're all successful doing this. What could the future look like out there on the Star Trek Enterprise? Well, there actually already are. You can see here, Great Ormond. They've already been working on how do I do pediatric fracture detection. So rather than have the person in rural Texas make a mistake about whether this was a child abuse or not. We have computers that can go, you know, this looks really like child abuse, or not so much, or yes, let's go get a second opinion. Remember my comments about focal cortical dysplasia? Yeah, it's highly unlikely any one pediatric neuroradiologist sees enough of these. But once you realize, boy, if I had every MRI image of every kid in the world for the past year, could I build an accurate AI algorithm to detect focal cortical dysplasia? And the answer is hell yeah, you could easily do that. This is actually work that's being done in England along this line. What about congenital heart defects? I probably said it, but 1 in 100 kids in the United States are born with a congenital heart defect. What if you could detect this fetally, right, before the mom ever gives birth to the kid? There is actually work going on at UCSF in doing this with ultrasound imaging. And so that now, whether you're in Willits, California, or Myanmar, or wherever, right, you can let this algorithm run, this agent run, and again, you could think of it as red, green, yellow, every patient, no matter where they are. I told you a little bit about FSGS. I'll just show it to you very diagrammatically. So these are 34 questions. You can't quite read it. Right, here are the questions. Here's the expected answers. Here's the confidence level. Here's what the testing would cost. So you just let the algorithm run, the agent run in the background against all the patients, grade them, as you see here, under 45, unlikely, 85 to 100, highly likely, and then you could see the different costs for the test. And so you could rank order again the test for FSGS. Here's a simple example from clinical trial. This is actually a clinical trial for a lung cancer drug converted into being a trial precise agent. So there's inclusion criteria, there's imaging criteria, exclusion criteria, and again, you can just let this run, the agent run, and then grade the patients as being eligible, ineligible, or somewhere in between. We are not only, because you can gather in all of this, our computers actually don't know where they are. So while we've launched this all around pediatric medicine, and that's our first focus, we know this is applicable outside of that. So MS is not a particularly pediatric condition. It does affect an interesting group of people in the world. And one of the things in MS is it's neurodegenerative, which means if you wait 8 years to find out you have MS, that brain damage has been done and is irreversible. So how can you do this detection much earlier? We are tracking actually 14 different research projects around the world who are using MRI imaging to be able to do early detection, all trained on small data sets. So we have just entered an agreement with the National MS Society that they are going to go run a fundraiser to raise $50 million to build an AI supercomputer for MS, 32 sites, all imaging machine data available, roughly 3,000 servers, roughly 2,000 terabytes of data flowing through it, all to perfect the art and science of being able to do early detection of MS using imaging, but also the same infrastructure can speed clinical trial development, remember back to digital twins of patients, and also can be used to pinpoint much more accurately which approved drugs would make more sense for the patient. So I'll leave you by saying I'm hoping I'm letting you think AI might be able to be used for good. And just teaser thing, we've been talking about this, building, large language models are great for text, but building them for medical imaging is going to require a whole new thing. Given what we are building, it is possible to start to consider the idea that we could end up with foundational models in medical imaging as well. So I'll end and then open it up to questions. If you want to know more, that's pediatricmoonshot.org, the website. We've been running a Pediatric Moonshot podcast series. In fact, I just did one this morning. all sorts of interesting people on here from CEOs of hospitals, heads of research, leaders in pediatric cardiology or whatever. It's on Spotify and Apple Music, Pediatric Moonshot. On the technical front, Bevel Cloud is the corporation that actually owns all the intellectual property for the distributed AI infrastructure, bevelcloud.ai. And then we have just started up a distributed AI podcast series really focused on all the different challenges of doing AI in a distributed world. I'm going to leave you with one last thing, which is what I leave my Stanford kids with. So I always end class the same way. I say, you know, all of you have been given a lot. You're here. And so if you've been given a lot, and I don't usually quote scripture, but to those who've been given a lot, much is expected. And so I always look at them and go, I expect a lot of you coming out of here. So with that, I will open it up to questions.
All right, let's give our speaker a hand. Yeah.
Thank you for, I appreciate your talk. It's personal to me because I survived a heart surgery for a rare heart condition.
Oh.
So being able to see how everything moves and the applications for modern technologies can be fascinating. So listening to my questioning, how do we build trust for these people with the inclusion of AI, both from a customer perspective and patient perspective? Some might not be well versed with AI or even understanding these technologies.
Well, I could also argue nobody really understands how GPS works either. So, but let me make the point a little bit differently. The way we're thinking about this is, we're not thinking about, is the world's best pediatric cardiologist at Stanford Children's. We think what we're doing could help them, but the real trick is where there's nobody, right? I'm like, I always say, if your mom works for Google and you live in Palo Alto, what we're doing is okay, it's interesting, but that's not most of kids in the world. In the United States, I just told you, rural hospitals, in cardiology, it's even more, 86% of the rural counties have no pediatric cardiologists. So nobody would have ever diagnosed in the field the idea that you have a congenital heart disease in the field. That would never have happened. The way we're thinking about it is, no, now it can happen because I can build a congenital heart disease detection algorithm that sits in a rural hospital in an underserved community, and it raises its hand. I keep arguing for red, green, yellow applications. Red, this kid has got transposition of great arteries. They ought to be on a helicopter for the local, right? Green, okay, we ignore it. Yellow, given the network we built, you could just go, hey, there could be something wrong. Let's go reach out to the expert at Stanford or at Lurie's Children's or whatever. Let them take a second look. So I don't think about it as much as, it's not about gaining, I mean, obviously we're working with a lot of the leading people to build something that is trustworthy from a technical perspective, we'll call it that. But I don't actually think about it as trust from the end user perspective, because today, there's nothing, right? And we can replace nothing with a lot better than nothing. But great question.
Thank you.
Yeah. Go.
Thank you for your talk. It's very eye-opening. My question is kind of about what you mentioned with using AI agents for the medical record scanned through the PDF. One big problem is like hallucinations. So how do you address that? Because coming to what you said about the chemotherapy, that the drug dosage, if there's a hallucination or something like that, it could have fatal repercussions. So what is the mitigation strategy in that regard?
Yeah, well, we're in the middle of that right now, but I'll tell you how we're thinking about it. First of all, the LLM on response to anything will actually point to why it said that. We're limiting scope. We're not saying, you're looking at all data. We're limiting scope to that which we RAG trained on it. So that's one answer to the question, that we can always go back to the original source and go, okay, is that correct or not? Now the questions that we don't know is, how big an LLM do we actually need to run? Because remember, we're running locally, so while we can put a lot of horsepower in place, it's not infinite. So, you know, do we need 10 billion parameters? Do we not? Maybe in the end, these become LLMs that are fine-tuned that just know medical stuff. These things we don't really know right now. But our early work in this says this is just light, even with hallucination, it's light years ahead of what anybody can do. And at least for us right now, everything is human in the loop. So when we say, oh, you might have FSGS, we're not telling the patient that. We're putting the medical record for the healthcare worker to look at it and go, you know, and with the logic for why this is. I think that the whole transparency thing is important, right? Let me explain why this is. And out of that, you know, produce more robust. But your question's good. It's one we've been focused on, right?
Okay.
Yeah.
Thank you.
Yeah.
Yeah, I want to follow up